right. Good morning, everyone. I hope you had a good night's sleep. And without further ado, it's my great pleasure to introduce Florian Wellmann, who's a professor at RWTH in Aachen, in Germany. And Florian has been working on geological uncertainty and Bayesian inference for many years. And I'm very much looking forward to your presentation.
Thanks, Guillaume. Thanks, everyone, for coming here in the morning. First talk, I know it's always a challenge after the conference. So I thought I'd start maybe with a bit of a story before we go dig into probabilistic modeling with a picture here. So I asked ChatGPT and DALL-E obviously to help me a bit with this presentation today, because the story it's about probabilistic geomodeling, but it's also a story about a golem and an owl, which is adapted, this metaphor here, from a brilliant writer and scientist, Richard Aylworth. But it's a very nice setup. Think of these two creatures that we have in here: a golem on the left side, this monster in the woods, which is very strong, a lot of power, but not that much of a brain. But it's very capable of doing things. On the other hand, you have the owl. Owl, known for intelligence of thinking, of looking ahead into the future, basically, which is sitting there, and they meet. And what we will see today in this presentation, how these two come together, hopefully, to produce really fantastic things. Let's get into science, though. What we want to talk about is the question of how we get to a picture of the subsurface, in our case, to a picture of reality. We don't know reality. We know it's somewhere in the subsurface. We have a certain set of features of rock types and whatever. And we know we can never only approximate this, clearly, because we cannot directly create a full model of the subsurface. And let's say, contrasting very broadly speaking, there are two ways in which we typically get to this approximation of reality. The first one, this here, the right-hand side, is something which we can call a data-driven viewpoint. This is very common in geophysics. We say, we go and we take measurements. This could be seismic measurements, could be gravity, magnetics, whatever you have. And you process this data in some form. You create what geophysicists then call images of the subsurface. And you may start interpreting. And of course, all of these steps, we've seen already some of those yesterday. And we see how AI, machine learning methods, help in some of these steps, especially also in the interpretation step. So that's a very common approach in geophysics, and of course also something that we see a lot in the AI world moving into. We have the left side, though, another kind of a very common approach, which starts with some picture of the reality in the form of a model. And if you think of the typical workflow for subsurface modeling, this could be your geological model, let's say, that is in the center here, where you describe basically in this model what you expect the subsurface to be like. The features in the subsurface, structures, and so on. You parameterize this model, you set up a mathematical model, and so on, and you get to your picture of reality. And in the end, of course, those two worlds meet. It's very contrasted here. But I would like to talk today about this left side, actually. So not about the full-fledged, let's say, maybe data-driven AI side, but really on this left side, because we look at here what we can call definitions of a bespoke model. So we define aspects of the underground that we think are relevant. And we combine this with inference engines, which allow us then to perform inference. And this is something which is well known also in the field of machine learning, not so much maybe in what you know, deep learning and so on. But it's actually in the center of machine learning in what is called model-based machine learning. What does it look like? We have some sort of an inference machine learning algorithm in the center. But we separate this deliberately into one part where we define a model, and there we define basically our specific requirements and assumptions about some features, aspects, in our case, the subsurface. But we separate, in a sense, the model from the inference algorithm itself. And then where we describe the model ideally with some sort of a compact code. So that we can basically put both things together in the end and to get to basically to inference and analysis of the subsurface. Very nice book about these concepts, model-based machine learning. It's been made famous by Christopher Bishop from Microsoft Research. and now a book where he's also co-author, which you can read online, model-based machine learning, with lots of these contents described in there as well, in the more general view, not so much subsurface only. But in our case, the big question is, so what is the right model for our purpose if we want to investigate the subsurface, geological modeling? And what is a suitable inference method? So these two things we need to look at, and this is what I will guide you through in the next 20 minutes or so. We start with part one, the model, and this is where our owl is coming in, as you will hopefully see, because the model, in some sense, is the part where we describe our view of what is important, your wisdom that you put into this concept, what is relevant to you, what is relevant to the question at hand. In our case, we looked at geological modeling. This conference is about mapping modeling. So many of the things you see here are what we had yesterday in the talk from Guillaume. There's surprising it's an overlap, maybe because we wrote this paper together. But this is basically about the question: what do we put into our model? And we know this from mapping. We had a discussion yesterday that we have maps, and the question: do we still need maps? Something which came up here as well. And I think one thing which we know intuitively, and if you are from geology, maybe not so if you are more from mathematics or machine learning, but when we create these models, they actually encapsulate a lot of geological history. If you think of a mountain range, or think of what we have below here, below us in Exeter, it's a long history, geological history, billions of years partly, with many processes interacting, sedimentation, tectonic effects, and so on, which finally led to the structures we see today. And it's interesting that we had many cases where we had more or less catastrophic changes, really sudden changes in time, sudden meaning maybe 100,000 of years or so, which encapsulates itself now in discrete boundaries, basically, in space. And so if you think of this not only as a convenient way to separate regions on a map or something, but these lines in 2D or 2D manifolds in 3D space, they actually encapsulate geological meaning, because we simplify this long history down to lines or to surfaces in space, but they do have a geological meaning. So this is the model, and we end up basically in the end with representations by boundaries, with a variety of data sets that we include in here, geophysical data sets and so on. I'll talk about those a little bit. But then the question becomes, so we can create these nice representations by boundaries. This here is an example where we see this outcrop, so we can go there and compare. In reality, of course, somewhere in the subsurface, we have very limited data. So we need to ask ourselves, first of all, how do we get these representations? How do we create these models to encapsulate the knowledge, basically? And how do we estimate uncertainties? So let's look at one modeling step that we are using here. This has been used a lot in different varieties. I saw this also yesterday. I'm talking to Guillaume with a bigger picture, even more approaches. What we use here is a specific implementation of an implicit surface representation, not going too much into the details, but it's a geostatistical approach where we use information from contact points, surface contact points, and orientation measurements in space. We combine those into basically the calculation of a 3D field, and then we extract surfaces of the 3D fields, as you heard yesterday as well, to get basically to our geological surfaces. And without going into more detail, there's a lot of work you can read up on here, go in here. Because one thing that I wanted to show you, so this is implemented, all the examples that I show here, implemented in an open source package, GemPy. That's a package we've been developing for some years now. So if you're interested to follow along with some of the examples in here, you can go ahead to the website. I hope the QR code still works. But otherwise it's on GitHub, so you can find it quite easily, and you can tell that it's a serious project because we actually have stickers. So if you like, you can also collect some of these stickers later here. It's the advertisement part over. Okay, so GemPy and the way to basically create these 3D representations. How does it look like? Well, this is an example of a model near Aachen, so where I'm located. Take away the surface, we can represent, of course, these nice layers of depth. We have here syncline structures, we have faults interacting with these geological features and so on. And it all looks nice. We can create representations here. In this case, in the side note, you can also link this to Blender, where we can actually create these nice 3D representations. It's very intriguing to think, wow, now we know everything because it looks so nice. but of course we know that this is not true, right? Because it's all based on limited data, on our knowledge that we include basically, and all of this has bias, errors, and so on. So the question exactly, how accurate are these representations? And one work which we also saw yesterday already, Claire Bond, University of Aberdeen, who's done these studies on interpretation uncertainty. This is a different work that we see yesterday. Yesterday we saw the example with seismic data. She's also done this example with borehole data, where she gave basically interpreters this data set, so a set of boreholes basically, and asked them to interpolate or to basically create a geological model out of it. And then placed all the results back into this cross-section, and what came out is basically this variability in here. And we see that, okay, where we have information, so we have boreholes here, it's all fine, the interpretations agree kind of, but if we move further away, we see quite a high variability in space, as you would expect. But of course, the point being here, this is something which we know exists, right? But the question is, what do we do in practice? Because of course we cannot always simply have, like in this case here, 19 geologists, partly very long experience. So we cannot simply go ahead in each project that we have and say we take 100 geologists and let them interpret a cross-section, and then we have this variability. That's difficult. So what do we do? And of course, a logical approach. Many of you, or most of you in this field of also applied statistics, will say, well, of course, let's try stochastic simulations. Something which we also we've been working on now in different varieties for many years. Before we look at the stochastic simulation part, though, let's look at the types of uncertainties that we can consider. Because there are different types. I mean, the first one is basically the position of our data points. If you like to think in the mathematical terms, this is the position of the kernels of our interpolation function, which may be uncertain because it's uncertain picks from seismic data, from borehole data, or maybe simply some place where you say, I assume my layer depth is somewhere over here, but we don't know. Then we have problems of interpolation between data points, which refers in the end to interpolation uncertainty, and also the question, how uncertain are you when you don't have any information? All the way to position number of faults. We saw yesterday the talk from Guillaume, the question of different fault realizations and fault networks. But what I would like to focus on today is really this type of uncertainty, but please keeping in mind that there are methods also to address these other types of uncertainties. At the moment, I'm leaving them out and focusing on this part in here. What can we do? Well, we have the stochastic simulation workflow. We have a set of input points. We have a set of input orientations. We construct maybe our initial model up here. And then, in addition to using this data, now we assign defined uncertainties of distributions. We treat all the variables, our input variables, as stochastic variables with a distribution. And then we can use any simulation engine basically to generate input data sets and multiple model realizations, and finally analyze and visualize the results. This may look now like this. It's a pretty old picture, but it still shows you, like, in this case now, instead of just having one interface for each of these boundaries here, say green one, I have now multiple interfaces, and this looks a bit like what we had in the example from Claire Bond. Although we have to ask ourselves, of course, yesterday this question of the trap to think that the model you're using is reality. Clearly, this is not the case, right? We have a system that we run, where we run the simulation. The big question is really, are these two now comparable? So do we actually reflect in our stochastic simulations the true variability that we would have if we would have multiple geologists interpreting this data set? And that's actually a very difficult point to answer, because mostly there are almost no data sets where we can actually compare that. There is one data set which is really exceptional from BHGM in France, who basically went to the same area in southern France for now more than 20 years for mapping and modeling. So there's a data set of basically 20 geological models for the same region. And in the study, actually, we went there and compared how this would look like, comparing the real mapped uncertainty in the end, variability, to our stochastic simulations. Still not published. I hope we get there at some stage. But that these are very nice results that at least show that we are not completely off with these methods that we are doing. So a little side note here, but what do we get in the end? We get realizations. Now I'm showing here, in this case, morphing between some realizations to get a bit of an intuition. See, we move these points up and down, and based on the configuration of all points together, we see how you get different realizations, and if the uncertainty increases, also the variability. Finally, we get to something where we may get very crazy, even overturning features in here, but showing you how quickly this can basically interact. And just showing, what I'm showing right now, they are 2D examples, but just to remind me as well, this is also working in 3D. Here a nice example in 3D, because it's early morning and we get something to look at. Okay, but this is, the point is, okay, we can generate now these realizations. The question is, how do we visualize those? Another side note here, looked at lots of different ways to visualize uncertainties. Also, the group of Guillaume, it's actually surprisingly difficult. I think there's this one paper where you also looked at even voice or sound, and things, people use even sound in 3D and things like that. It's actually quite tricky. One method that I still think is really useful is entropy, and I'm showing this here because I showed some of the plots a bit later. These entropy plots, basically, where we do it in a discretized version, so each cell, which is in this case black down here, has zero entropy, meaning that all my realizations show me the same output. And if I go to higher and brighter colors, simply means that the information of the cell is more uncertain. There are more possible realizations. Okay, but let's move on. The point though now, we have our stochastic simulation. Nice, we can generate these models, we can let them wobble around in 3D. What could possibly go wrong? We can stop here maybe, but of course not, because what can happen? Well, let's say we look at this simple cross-section in here and we generate a realization. Things looks like a bit like a normal fault, offsetting some sort of a layer in here. What we expect is that we get something similar, maybe a different tip of a fault, different tip of this layer, but this is okay, we would be fine, and this is maybe the range of our variability. What can happen though is that you simply move points in such a strange way that your model construction fails. And to all of you, who've ever tried using things like GeoModeler, Leapfrog, also GenPy as well, this happens very quickly and you get these blobs in space, which look really weird. But this is fairly easy to pick out, at least. What is more tricky sometimes is that you may get something which we call here failure of model constraint, because it could happen that, in this case, see here the fault shifts from a normal fault to a reverse fault. And this would, of course, have a very different implication for the tectonic setting. Quite difficult to pick up, but the main point, though, is that what happens here, we have an engine where we automatically generate these realizations, and this engine, of course, does not have geological understanding per se. What it means statistically is, of course, that it's not respecting correct parameter correlations. We may need to do a final evaluation, and it's actually really interesting if you generate these models in cross sections and you show them to a geologist. She could directly say this makes sense, this does not make sense. It's actually quite difficult to teach computers to do that, and this is what we talk about next. Because what we propose here in the end, on this type of work, and not only us, but everyone working in this field, to say that we create these models, but really we should consider each model only as one possible hypothesis. Okay. And we need to have ways to discard models that are geologically or geophysically impossible, which in the end means we describe models with random variables and distributions, and we need to estimate parameter distributions and correlations. Putting this all together, we want to quantify uncertainty as well. And if you put all of these things together, then this gentleman here pops up, Thomas Bayes, the English clerk, who set up this idea that he wants to prove the existence of God, which did not really work out. But at least it gave us what we have today as the Bayes theorem, which is the foundation of all kinds of probabilistic inference as well. And the point is here that we should consider geological modeling as a probabilistic, model-based machine learning problem. What do we mean? Probabilistic machine learning here, just another side note. So we extend this idea of model-based machine learning with the probabilistic aspect, where we treat unknown quantities as random variables. Let me move on quickly in the interest of time, because we go to the second part, the inference engine, which is now our golem. And the golem, remember, is this basically this creature which is very strong, very capable, but follows simply your instructions in the end. And this is what we want to look at with a simple example here. How does this look like? Assume this case here where we have, again, think of this as a, sorry, missing here the axis. This is depth or something. So we have here a cross-section through a vertically cross-section with two interfaces, this blue and this green interface. And each of those is uncertain, and we describe the uncertainty here with this distribution. Now let's assume that we know from some other area, we can generate realizations, and you can see now that we randomly draw realizations from these distributions, and we get quite a variability of possible realities. Let's say that we have some additional information. For example, you know from observations in the vicinity that this layer in between these two interfaces always has a thickness of maybe 150 meters plus minus 30 meters or so. What we can do is now we combine those two pieces of information, our prior assumption about the depth of these interfaces, but we combine this now with the knowledge that all our realizations should, on average, follow this distribution that we have over here. And if we put this into the inference engine, in this case here an MCMC, Markov chain Monte Carlo approach, and we end up with now new distributions for our expected position of the interfaces. You see the lower one is now greatly decreased. But also, one point which is maybe not so obvious at the beginning, but you now see if we generate these realizations, it still moves up and down, but the layers move more or less in parallel. Because the system in the end learned that my realizations should follow this thickness curve that I have in here. Statistically, this is clear. And what is happening is, of course, that we're not just estimating parameter variances, but also covariances. So we get from independent correlations now to the posterior correlation, which is very high. The point being that our system in the end learned to incorporate this information, and we now generate new models, and they follow this additional information that we put in. What does it look like in the theory? We move through this very quickly. Bayes theorem, we have initial model parameters, we have measurements, and these likelihood functions. And this is all nice if you write this down for a simple equation, and especially discrete distributions, you can solve this very easily. It gets more tricky for continuous variables, and I'm showing here a diagram just to show you this. You can also draw this in these so-called graphical models in here. I'm saying this because we get a bit to more complex models in a second. So this is if it's very simple, then we extend this to multiple parameters. Still fairly simple because it's simply only a product and sum in here. But for all of those who know a bit more about the theory, the tricky thing is that we have this integral down here, which is actually quite difficult to deal with in practice. And this is where now it gets a bit difficult with this inference engine, our golem. Because the question is really how can we get to these inferences in a practical way? And there are many approaches around. Luckily, we have now a lot of golems in probabilistic programming frameworks. Famous ones, Bugs, Infernet, PyMC, for example, but there are also now many implemented in machine learning frameworks, TensorFlow and PyTorch especially. This is the one we're using in GenPy now in the meantime. We used to use Theano. And also domain-specific projects like UQLab from ETH and Coffee from Australia, which also enable you to do these inference methods practically. Okay, usually required, as a little side note, differentiability. I'm not talking about this here today, it's also a small side note. But if we want to use these methods efficiently, we need to write our forward models, so our geological modeling code, in a way that we can automatically differentiate this code, like in many machine learning approaches. And this is where all these frameworks like TensorFlow, PyTorch, and so on help immensely because they do this for us automatically if we write the models in a suitable way. And this is done in GenPy. So if you use GenPy, you can differentiate the entire code. Okay, let's move forward to geophysics, but in the interest of time, I'm going quickly because I think it's over.
No, you still have time.
I'm
very sorry.
Because I was a bit at the, okay, good. Then now
we have 6 minutes for you to finish and for questions.
Okay, wonderful.
Sorry about that.
Thanks, Guillaume. So we link this now to geophysics. What do? We make our graph that we have in here. Remember, this is our prior parameters, observations, and all these arrows basically are inference steps if we do backwards. We make this more complex by adding geophysics to it. And what does it end? Probably also rock properties, of course, in this case, and other types of properties that may come in. Which means in the inference engine, we need to generate now realizations of the geological model and the geophysical response. And let me go through this very quickly here, just an example from the greenstone belt. Sorry, skipping those, I'm going to the results directly in the interest of time here. But what I want to show you, is the results, only to show you that this is possible in practice. What we see on the left-hand side here is a cross-section through a model in Australia, a greenstone belt model, without any details here. But the point is that we generate random realizations. You see that we get above here, this is the cross-section through the model. And we see that we have this double folded layer in here, which is kind of what we expect. But it has some strange artifacts down there. We see that we have a mismatch to forward gravity, because between calculated and measured gravity in the end. And we see down here we have the entropy, we see it's a wide range of uncertainty that we have in space. Now if you combine this with gravity, with the geophysics information, we see that we reduce the misfit. Sorry, the color bars are messed up over here, but just for the purpose of introduction here. We reduce the misfit, we see that we also reduce the uncertainty in space. But we now get realizations that are actually geologically wild, so don't make any sense anymore, because suddenly we get very strange topological contacts in here. So if we combine this now with also geological likelihoods in the end, so saying that we have also people looking at this and defining what is reasonable and what is not in geological terms. So in this case, we actually talked to the geologist who created this initial model and asked her, so what do you think? How would you judge one of these realizations? And we formulated this in the form of geological likelihood functions, and now we see that we actually get models that fit a bit to the expected setting with a double folded layer in here. Gravity misfit is increased. So in the beginning you think that's odd, we add information, but we increase uncertainty. Also here in space, and in the beginning I was very puzzled, but of course what happens is that we have our models, our bespoke models. They represent what we know, what we expect, but we may miss some features clearly. So this is the point that, of course, adding information will not always reduce uncertainties, but definitely will force you to rethink your models. Okay, a little side note. A lot of these gravity calculations can be time-consuming. One really nice aspect of these implicit representations or these continuous interpolation functions is that you can evaluate them anywhere in space. So what we also worked on is so-called sensor-based grid inversions, where we really consider the position of each gravity measurement. And at this position, a very high resolution of the model, and outside we reduce the resolution. So just a very efficient way to generate these models. Brings me a bit to the end, a bit of an outlook. What I showed you here are some components of the OWL, the model basically that we generate. We talked a bit about the inference engine, but all of these things, of course, can be extended to many, many more complex aspects. For example, the geometry, we can look not only at implicit representations, also explicit representations. There are many new ways which come in the field of machine learning. I have this, yeah, okay, here, because this is Mike's work, which we will see a bit later today, GeoINR. So we have many ways to generate these models more efficiently. We can include statistical fields, so also distribution inside these domains, basically. There are also aspects to consider variational processes, Gaussian processes in here. So a lot of work happening in the basically definition of our models at the moment. Also in the integration of data, so we link this typically to geophysical forward simulations, but could also be geothermal simulations. That's the field I'm working in mostly. As a side note, which allows us then to combine uncertainties both in the geological model and in the process simulation. And finally, we can link this to decision theory, because in the end, all uncertainties are nice, but they don't matter if they don't influence a decision, right? You can make nice models of uncertainty, but they may not be relevant at all. The question is always, what is the decision that is behind it? And there's an interesting link to Bayesian decision theory, which you can combine with these models. Ongoing work, I would say. And entropy. For those of you who know me, favorite topic, but I'll skip this in the interest of time. Elephant in the room is practicability, because this is actually something, our golem is powerful, but there are, many challenges also still. Leave this here also out, but just as a side note, so what we work on mostly is Hamiltonian Monte Carlo methods based on the differentiability of our code. There are also many new ways, Stein variational gradient descent methods and so on, which allow you to get to inference a bit more efficiently than we can with standard MC, also a side note here, also some things we've been working on. Finally, summary, no, sorry, the time. We talked about the golem and the owl here. My main point, of course, we're here at the AI conference. What I talk about now looks like a step back maybe, because I'm telling you that maybe putting everything into a big model and pressing a button, I know that you look at this in detail here, but that this is maybe not necessarily the right way. It depends on the problem you're looking at and the data that you have. So I think there's a lot to thinking about, including knowledge that we have into a model and using this model in an inference way. And this is my main point. This is possible. You know, don't think about a geological model as one reality. It's always just one hypothesis of many possible realities in the end. But we can include this into inference models. Always be aware that the range of plausible models is not a plausible range of models. My favorite quotes by Gray Nearing and Shoshin Gupta. And the question is always, what is the best way to combine information, I think. Many tools, many golems, many methods. Very exciting time in the field of AI and geosciences. So this makes also this conference so timely and the meeting here. And we didn't even talk about LLMs here. So this is something which is the continuation of there. Maybe we'll see what is happening in this field as well in the future. Thanks for listening.
You used all the time. I don't know how flexible we are, but maybe we have time for one short question and short answer.
Yeah, absolutely.
Short answer.
Quick question. The geological models and properties are uncertain. Your geophysical field that you're looking at, your observed field, is that also considered to be uncertain as well?
You mean the processing of the geophysical data? Well, that's in the yes. That's a likelihood function that you define for the geophysics, basically. But if we look at really information at the centers, we can get rid of all of the processing, and not all, but to a certain degree, for gravity, for example, instead of doing all the Bouguer corrections and so on, we would use directly the measurement at its position. And this reduces also a lot of the bias that you can put in the geophysical processing. So, but if you don't have this, or if you have uncertainty in the geophysics, yes, you would use this in the likelihood function. So you define for the likelihood function how you connect the data basically that you have with your hypothesis. Yeah. But no,